Hello everyone, nice to see you guys. Let's wait a bit, maybe more people join, and then we continue our discussions.
Good afternoon, Professor.
Hello. Okay, guys, who wants to join will do that along the discussion. And I believe we continue further our discussion on the topic of mechanical waves. So just to remind a bit at which point we stop, we derive the equation which describes the location, like displacement of a string along which some sinusoidal wave is spreading. And we did that as a function of two independent variables, x, position along the string, and time. So, and we have shown that this is a periodic equation which describes this sinusoidal wave with certain parameters involved, like wavelengths, distance between two adjacent points with the same phase of oscillation of the wave. For instance, could be convenient to measure between two adjacent maximum or two adjacent minimum. And also the time period of the wave, which is required for the wave to transfer, to be, to travel along the distance of lambda, which is wavelengths. So that's why how we define the velocity, like speed of spreading of this wave. We divided lambda by period wavelengths of the wave and divided by period of the wave. And that gives us the speed of moving wave along the, it actually applies to any cases, but in particular, we are discussing the specific case, which is sinusoidal wave, mechanical wave spreading along a string with certain tension. Okay, so now let us proceed further, and I guess we will start from writing down again this equation which we derived for the sinusoidal wave, and go further with the analysis of this equation. Okay. So let us first write down this equation. So it's y. I don't write as a like function of x and t, just y equal to a amplitude of the wave, sinus 2 pi times x divided by lambda minus, t divided by the period. Okay, so this is the equation which we derived, and now in order to make it more applicable and convenient for practical usage, we introduce the following substitutions. So first of all, kind of important, you will deal with this parameter in future quite often. It's k, so-called angular wave number, or usually called just wave number, and it's equal to 2 pi divided by lambda. It's very common parameter, which is very often used in any field related to waves, spectroscopy, and stuff like that, from characterization of mechanical waves to some material science, where you also characterize different spectra of absorption by molecular vibrations or stuff like that. So anything what is related to waves, mechanical or electromagnetic, this parameter is quite common. And also, we already know this parameter, it is angular velocity, or I mean, in this case, it's angular frequency for oscillations. And it's also 2 pi divided by period t. Okay, now taking into account this, we can rewrite this equation. So it will be y equal to amplitude times sinus kx minus omega t. So we just open this parenthesis and we have 2 pi times x divided by lambda, and 2 pi divided by lambda is substituted by k here. And then we have 2 pi times t divided by period. So 2 pi divided by period is substituted by omega. So this is equation for the sinusoidal wave, which is almost in its final form. However, it's just similar to the equation which we derived for harmonic oscillation motion. We need also take into account that it can be in different initial phase. So not necessarily that y is equal 0 at t equals 0. So in order to take this into account, some phase shift initial, we need to add phase shift phi. Then the final expression for this equation will be a times sinus kx minus omega t and plus phi. Okay, so this is the general form for the sinusoidal wave equation, which describes sinusoidal wave. To be more specific, displacement of elements of the string along which sinusoidal wave is spreading as a function of x and t. location and time. So since we have the equation which describes position, obviously we can use it to determine velocity and acceleration. So let us do it. So we know that velocity is the first derivative of position, dy over dt by time. And keep in mind now that maybe I will write this to be more specific, xt. So this function is not just function of t, it's a function of two independent variables, and we take only derivative over t, assuming that x is constant, it doesn't change. That's why it's called a partial derivative. Means we take derivative of a function which depends on two independent variables, but assume one of these variables constant and derivate only for the other independent variable. That's why, in order to highlight this fact, instead of it's reading like we should write it like this: dy over dt. And now, assuming that x is a constant, we take derivative. So derivative of sinus, it will be minus cosinus. Then we have a times, let's put this minus here, cosinus kx minus omega t plus phi. And then we also need to multiply this. Yeah, excuse me?
Excuse me, Professor. Derivative of sine is plus cosine, or I think it's plus.
Derivative of sinus is cosine minus cosine, and derivative of cosine.
No, I mean,
sine.
yeah. Derivative of cosine is minus sine.
We did it before. Let's check it just to be sure. Derivative of cosine sine. Yeah. So derivative of sinus, cosine x, and cosine minus sinus x. Yeah, okay. Then, but it's a bit confusing now. Should we have this minus here? Dy minus. Yeah, apparently we don't have minus here. Okay. That's but then cosine minus sinus. Okay, everything is fine. I was confused with this minus. Initially, I just remember it has to be here, but it actually comes later. Okay, never mind. Thank you for the comment. It's derivative of sine is cosine. Then we continue taking the derivative. And here we don't have minus, but then we take derivative of the argument of the cosine. And this one is constant. This one is constant. Then derivative of this argument will be minus omega. So minus omega. Yeah. And now we can write it in a more compact form. Will be minus omega a times cosine kx minus omega t plus phi. Okay, so this is the expression for the velocity. Now let us maybe copy this, like rewrite this equation on the next slide and continue further, because we need to take one more derivative of dv over dt to take the to get the expression for acceleration. Okay. Then a acceleration is equal to dv over dt, or it will be second partial derivative of dy, like y of our like displacement over time, d square y over dt square, and this will be the following. So we need, yeah, let's write here this equation. How was this? Minus, okay. Minus omega a cosinus kx minus omega t plus phi. So this is our equation. We need to take derivative over time, partial derivative over time. And now we have derivative of cosinus, it's minus sinus. Then we cancel out this minus. It will be omega a sinus kx minus omega t plus phi. And again, we take derivative of the argument, which is times minus omega. And as a result, we get minus omega squared a sinus kx minus omega t plus phi. Okay, so now we have expression for the velocity and acceleration. So we see from these equations that maximum values for both of these parameters, maximum is obviously like this omega times a. We just take absolute values like. And also maximum acceleration is omega squared divided by a. What is important to mention, that they don't reach their maximum. I forgot to write here maximum. They don't reach their maximum values simultaneously. So you can take a look for or write together all these three equations for velocity, acceleration, and position, y. So maximum velocity will be reached at position y equals 0, and maximum accelerations will be reached at positions plus minus a, so at amplitude values. Okay, so this is pretty much everything what we had to do with this derived equation for the sinusoidal wave, which is spreading along a string. And now let us try to derive how the speed of a wave depends on parameters of the string. So that is another interesting point when we try to find a correlation between spreading this mechanical disturbance, which we create with harmonic oscillator, means sinusoidal wave, with the properties of the medium. In our case, it is string. And let us just think a bit before we proceed with some equations. So if we provide some disturbance, let's say we pull sideways, like up and down the end of some string, we create, and there is some tension in the string, obviously. So now if we consider just very small element of this string, its acceleration, so this disturbance creates some string in the some tension in the string. So the acceleration of this very small element will be proportional, obviously, to the tension provided, because it's only one force which acts on the elements of the string. So definitely the larger tension in the spring, the larger acceleration, and eventually it will end up with larger velocity, like speed of mechanical wave. So we can write that based on this assumption, velocity, like speed of wave along a string should be, I mean, not equal, that's too early to write equal, but should be proportional to the tension in the string. So from other side, the acceleration, if we have, let's say we fix this tension, then from other side, the acceleration will also depend on the mass of this element. The heavier the element of this string, the smaller acceleration will be at a given tension. Means that the speed of wave, this mechanical wave, will be less. And we cannot, since we have linearly distributed medium, it's convenient to consider some linear density of this string. So let's call it mu. So it has units of kilograms per meter. So this linear density, if it increases, the speed of wave should decrease. So obviously, based on these assumptions, which actually only are based on the second law of motion, the speed of wave should be reversely proportional, so proportional to 1 over this linear density. So we expect to get something like this. So speed of mechanical wave should be proportional to tension and reversely proportional to the linear density. So that is based just on our phenomenological consideration of this effect. And now let us go to the more accurate quantitative derivation. So for this purpose, we need to consider just one pulse, which is spreading. It doesn't actually, we'll see that it doesn't matter which shape of the pulse is it. So it could be sinusoidal or some other shape. But now we just consider just random shape pulse, which is spreading along the string. So we have some pulse. And we have a small, consider some small element of this string. Let's say it's delta S. It's not clear that it's S. Delta S. Okay, and this pulse has to move along this string, so with certain speed, like velocity, from the left to the right. So now we can, let's consider first a system of coordinates which is connected with the ground, y, x, and in this system of coordinates, each element, as we know from the definition of waves, we have transport of energy, but we don't have transport of mass. So it means that each element of this string, is stationary. It doesn't move with respect to axis x. So it moves only in y direction. And with respect to ground, with this like stationary system of coordinates, the pulse is moving with speed v from left to right. Now for more convenience in further derivation, we need to consider another system of coordinates. I will just schematically show it here. It will be y, x also. But this system of coordinates will move from the left to the right with velocity v. So it will move in the same direction with the same velocity as the pulse is doing. So with respect to the pulse, this mobile system of coordinate will be stationary because it moves together with the pulse. However, with respect to the elements of the string, it will move to the right. Means we can consider that elements of the string are moving with the same velocity v, but to the left with respect to this mobile system of coordinates. And now let us, taking into account these considerations, let us enlarge this area in a new image and proceed with some calculations. So when we enlarge this, let's say we have this small element of the string. It possesses some curvature because it's part of the pulse. So let's draw here some horizontal line as a reference. And this will be, this element will represent some arc, like as a part of the circle with radius r. This is our radius r. And it will stand on certain angle, which is formed by this radius r. So if we consider this part, it will be theta. So total angle will be like here, it will be 2 theta. So now, what forces are acting on this element? We have only tension. And tension acts from both sides, from the left, from the right, along the string. So it will be directed something like this. So we have tension and tension. And this angle between horizontal line and the direction of the tension and tension vector will be also theta, because if we have right angle here between horizontal and vertical lines, we also should have right angle here. So if we move it by angle theta, so between this radius and vertical line, we have angle theta. That means between horizontal line and vector t, we also have angle theta. And here it's also theta. Okay, now another factor which we need to take into account is mass of the element. So we mentioned that it has some length delta s, and we have certain linear density mu. So mass of this small element will be equal to the product of mu and delta s. Okay, now we have our model, which we need to analyze now. So with respect to the mobile system of coordinates, this one which moves to the right, this element, since the string is immobile with respect to the ground, will move with velocity v from the right to the left. Does it make sense? I hope yes. So we have mobile system of coordinate which moves with respect to the ground and this string to the right, means that parts elements of the string with respect to the mobile system of coordinates are moving to the left with the same velocity v. So when this movement happens, since it's part of the circle here, this how this segment, this element of the string is forming an arc of this circle with radius r, and this element is moving with some linear velocity, means that it will experience some centripetal acceleration. And this acceleration will be equal, as we know, v squared divided by r. So now we need to take into account that this centripetal acceleration should originate from some force which causes this acceleration and causes the movement of the element of the body along the circular trajectory. So in this case, it will be components of tension vectors. Since they act on this element in both directions, so we have one acting at this edge from the left, one acting at the edge from the right, the horizontal components of these vectors will be compensated by each other. And the, let's call it radial component, which goes to the center of this curvature, will be represented by such equation. So we have the radial force equal to two components, like vertical components of these tension vectors. It will be 2 times t times sinus theta. We have this angle theta, and that's why horizontal component will be t times sinus theta, and we have two of them because there is tension from both sides. It will be 2 times sinus theta. And assuming that we have a small element and this amplitude value of the maximum value of the peak is not very large, so it's not very intense disturbance, this theta will be small, and we can substitute sinus theta with theta for small theta, which, as you remember, we gave this definition. It's if theta is smaller than 10 degrees, like 0.2 radian, then this approximation already becomes valid. So that's why we can write that it will be equal to 2t times theta. Okay, now we need to express the mass also in terms of theta in order to proceed further. We know that mass is equal to mu, linear density, times the length of this element of the string, delta S. Also, how can we relate the delta S with theta? So we know radius, we know theta, so we can calculate the length of the arc which stands on this angle, which actually 2 theta, because we need to consider whole angle. And in this case, it is delta S is equal to the product of radius to the total angle here in radians. So it will be r times 2 theta. And that's why we can write for the mass that it will be equal to 2 mu r theta. Okay. Now, this radial force is, according to the second law of motion, we can write that Fr is equal to ma, and a is centripetal acceleration. So we can write this equation here. It will be m times v squared divided by r. Good. So now we write, instead of fr, this equation, and instead of m, the mass of this element, this equation. Let us do it. It will be 2t times theta equal to 2 mu r theta times v squared divided by r. So what we get out of here, we cancel out our radius, we cancel out theta, we cancel out these two. That's why from here we can write that v, the speed, is equal to square root of t divided by mu. So our first assumption, based just on considering the physical model without any quantitative calculations, assuming that we know second law of motion, gave us quite good prediction. We mentioned before that speed of spreading this of mechanical wave along the string will be proportional to the tension in the string and reversely proportional to the linear density. So it just within this square root, we couldn't predict this dependence. So that's why we need to develop more accurate model and do this derivation in order to get the final equation for the speed. And that is very important, that in this final equation, we don't have any information about the shape of the pulse, and that's why doesn't matter on the shape of the pulse, the speed of this, of any mechanical disturbance along the string with certain tension and molecular, this linear density will be defined only by tension and linear density, independent on any shape of the pulse. So it really will be defined only by the properties of the string. Okay, so I guess now we are done with this derivation for the velocity, like speed of mechanical wave spreading along the string. Next, we will consider the reflection and transmission of mechanical waves. So maybe we can just start introducing this topic during last few minutes of our today's discussion, and we will continue this during our discussion on Friday. So definitely, if we have some string attached to an immobile object, let's say some wall, and we generate some mechanical disturbance in this string, which moves towards the wall. Then when it reaches the wall, let's say here, it will interact with the wall, and in this particular case, there will be some force originated from the pulse exerted on the wall, and it will go upwards. So this will be the force which pushes the wall upwards. And according to the third law of motion, the reacting force, the reaction force from the wall to the string will be oriented downwards. And because of this will be kind of a generation of this reflection event. It will be like equivalent to wall pulling down the string. And in this case, the reflected wave or pulse will change its direction from going from left to right. Now it will go from right to left, but because of stationary fixed end to this wall, the phase of this pulse will be inverted. So it will be, instead of positive displacement y, will have negative displacement y. So it means that the reflected wave will be inverted. It will change its phase to the opposite. However, this will be true not only for, so it will not be true always. It really depends if this end is fixed and cannot move, or it's fixed and still can respond to the mechanical disturbance and move together with the pulse. So if that happens, the reflected wave will not change its phase, and reflected wave will not be inverted. So it will come with the same displacement, positive or negative, depends what is initial pulse, but the reflected pulse will not change its phase. So it will be not inverted. However, we will talk about this in more details during next discussion, and also we'll consider reflectance and transmittance when we have some interface between two different strings, because one string can be thinner, another can be thicker, so they will have different linear densities, and always at the interface some interesting effects are happening. In particular, for the most simple example from mechanics, we will get some reflection and transmission of mechanical wave, which is approaching this interface from one side or another. And moreover, this reflection and transmission will depend from which side this wave is coming, either from the thin wave, thin part of the string, or from the thick part of the string. So this kind of interesting moments we will discuss in details during our next class. Okay, guys, I think we are running out of time. Thank you very much for attention. and following what I'm doing there, because you see, and always do some mistakes. Thank you for bringing this up, and have a good evening. Oh, there is a question. Yeah, my dear.
Excuse me, Professor.
Mm-hmm.
I wanted to ask one question regarding the formulas that we derived.
Yeah, sure.
So the question is about formulas for velocities. Like first formula from the derivative of dy dt, like minus omega a cosine kx minus omega t plus phi.
Yeah,
And
okay, I will just go to the screen so we can see. Yeah, so this one, which is
yeah, this formula and the last formula about the speed. So how they differ between each other?
Yeah, good question. Yeah. So as you see here, we take derivative in order to get this velocity, the first one. We take derivative dy over dt. So means this is velocity of an element of a string which moves up and down with the wave, so along axis y. And the expression which we derive here for the velocity. So this is different velocity. This is speed of the wave or pulse moving along the axis x. So the first one is the speed of elements of the string moving up and down. And the second one is technically the speed of moving the pulse along this string, means the speed of moving, let's say, mechanical energy along this string. So they are not the same speeds.
Okay, thank you.
You're welcome. Okay, thank you for your attention. Enjoy your evening and take care. Bye-bye.
Goodbye, you too.